Hello there everybody and welcome to Lecture 4 of Introduction to Forensic Science for Healthcare Professionals. We are not meeting in person as I have announced on Blackboard a little bit earlier ahead of the actual lecture, and I hope that most of you got that notification. Thanks to one of your colleagues who was brave enough to contact me ahead of this lecture. I was notified that you guys have an upcoming exam at 5 p.m. and that was a majority of the class that was affected by that exam. So I decided, instead of having a significant loss in attendance for the lecture 4, that instead I would record the lecture and deliver it online and give you guys therefore an online attendance and the opportunity to listen to the recorded lecture. So that obviously sets us up a little bit differently with the schedule, but let me go back a step and first wish you all a happy and healthy New Year 2018. I hope you had a chance to relax and step back and really enjoy the break with your loved ones. Go back and hopefully your travels were safe and without any impact to you, and that you also didn't catch anything and were sick over the break. I know a lot of folks got sick over the break, caught a cold or even worse, a flu or something like that. Fortunately, I only got a little bit of a cold and then for the most part was unaffected. I spent part of the time in Colorado and then came back to Arizona. So, excuse me. Just to get back to where we at now. So we had our first 3 lectures last year, and the first 2 I already delivered online. So we only met in person once so far, which is obviously not how things are usually done at Midwestern. I'm more used to that at the University of Florida, where I deliver all of my lectures pretty much online. So this is not unusual for me, but just to make certain that we're all on the same page, this should be more of the exception for how you experience your lectures at Midwestern, at least at this point. So we have decided as a class, or I have decided based on a Facebook poll and a majority of you being affected by an exam tomorrow, to give you the time to prepare for that exam, to schedule this lecture 4 online as well, which leaves us with lectures 5, 6, and 7 in person, and hopefully give us some time to also have some discussions in class, because obviously I would enjoy our in-person discussions as well. I had to schedule one more lecture online, which is lecture 8 on February 6th. So this one will also be delivered online. I apologize for that. I have to travel out of town. But rather than to reschedule it and mess up your schedule, I decided to deliver that online and record it as well. Which still leaves us with lecture 9 in class on 2/13 on February 13th, and then a half-hour lecture, limitation and or prevention of illicit drug abuse and trafficking, lecture 10, which is a half-hour lecture, will still be delivered online, recorded, with the final exam, which we have agreed on for Friday, February 16th, will be a take-home online exam, which will be available to all of you during the whole day for February 16th. Okay, so that sets us up for at least 4 classes out of 10. 1, 2, 3, 4. No, actually 5. Half of the classes will actually be in person. I hope I'm not getting dinged for this by the administration, but as long as you guys are happy with the way things are going, I guess we're gonna be fine. However, I just want to let you know I am still available to answer your questions. I will be on campus still on the Tuesdays that we have the in-class sessions ahead of the lectures. So if you have any questions and would like to meet with me in person ahead of the lectures, then please feel free to approach me. So, what are we talking about today? Lecture 4 is on the techniques used to analyze biological and chemical evidence and trace analysis. So we will be talking today about analytical techniques. And this is something that some of you may be familiar with from your undergraduate studies, especially if you studied chemistry or forensic sciences or some other more involved natural sciences. Others may not be as familiar with some of these techniques, but at least some of the basics may be familiar to you. So let's first distinguish between chemical and biological evidence. When we talk about chemical evidence, we usually refer to drug powders, unidentified substances. It can be medications such as pills or even something like fluids that are taken. It can be explosive precursors for illicit drug synthesis, so something that can be in solid or in an aqueous or fluid state, or even in a gaseous state. Sometimes it can be environmental, synthetic, and inorganic toxins. We always have to assume, though, that when we look at chemical evidence, that it might be toxic or have some adverse effect on the body, and therefore we need to take protective measures, especially when it comes to something like a crime scene, or even when it comes to something like medications that might have adverse effects. So exposure to something like a white powder substance obviously requires you to have personal protective equipment, which is often abbreviated as PPE, personal protective equipment to wear. You as a pharmacist may wear something like gloves or sometimes safety glasses. Sometimes you may wear something like a mouth protective mask, a mouth mask or something like that, a mask to protect your mouth or your breathing. In most situations you may wear it because you are for example, have a cold or something like that, but it may also be because you don't want to breathe in something like a dust that emerges from a drug powder that you are filling into a container or something like that. In contrast to that, we've got clearly biological evidence: semen or vaginal fluid, sweat or skin cells. This is clearly biological evidence because it's usually used to extract DNA. It is not used to derive chemical evidence, so meaning we wouldn't use it for deriving drug or for toxicological analysis. However, we have an overlap between the two. Plant material, for example, such as cannabis or kratom, which I'm looking at, or even a coca plant, which derives cocaine, or opium plants, which derive morphine and opium itself, are kind of a crossover because they are biological in nature, but they are used to obviously extract chemicals from it. On the other side, we often use blood, urine samples in order to do chemical testing on them for impairment or even post-mortem testing to look for evidence of intoxication or contributions to the cause or manner of death. The same is true for hair and tissue samples, especially when it comes to prior exposures to toxicants over a longer period of time. Hair, for example, can give us indications if somebody has been exposed or taken drugs over a longer period of time, or not an acute but rather a chronic exposure. The same is true for tissue samples, for example, exposure to alcohol. If we have chronic hepatic encephalitis or chronic liver failure or nephrolithiasis, where you have a kidney damage that occurred over a longer period of time. And then we have rather unusual evidence like insects, for example, that sometimes are being used but rarely used to derive chemical evidence, where, for example, some larvae store unique metabolites of morphine. Morphine sulfate, for example, or certain glycosides of morphine that are not usually found in humans, that are stored in larvae, for example. And soil obviously can sometimes give indications. This is more in decomposition cases, in advanced decomposition cases, where a body has been, for example, buried for a longer period of time, and some of the soil may contain degradation products of certain chemicals like lead or arsenic, for example, which are more of an inorganic toxicant. Most of the organic toxicants may be decomposed by that time period already. So when we look at a collection and initial evaluation of evidence, there are collection evidence kits basically that are being utilized, and where we mark basically everything. Most of these contain personal protective equipment and then various different markers and evidence sheets, and how everything is kind of has to be marked and indicated, and who collected it, and so on and so forth. What has to be done during the collection stage is to ensure that the location of the evidence is recorded and description of shape and physical state of evidence. This is important for some of the evidence that might deteriorate fast over time, or that is prone to change. So if something is hygroscopic, for example, it might change its state. It might change from a solid to a fluid state over time if it's hygroscopic, because it attracts water over time. Ensure that the evidence is collected in appropriate containers. That is especially important for biological evidence. So if you collect something that is still wet and you collect it in a container that is sealed completely off, like a plastic container, then it might rot over time. It might attract mold over time. And then obviously you might lose an important piece of evidence. So in most cases you want it to dry out, especially with blood stains. You want it to dry out so that it is preserved in a state that can be used. Once it's molded, or once it is kind of decomposed in a state that it cannot be used any longer, then you might not be able to use that evidence because it's not preserved in a state that it can be used. Chemical corrosives require special containers and sealing. A chemical corrosive can be stomach acid fluid, for example, which you don't want to put into anything that contains plastic or simple paper. So that's something to consider, but chemical corrosives can also be acids or bases. Biological evidence is always considered a biohazard, and therefore there is a risk of disease transmission, especially if you have needles or anything that is sharp. It needs to be bagged or stored accordingly. And the initial evaluation of evidence sometimes takes place at the crime scene directly if there's time and sufficient manpower. In most cases, it will take place at by the crime scene investigation team when they back in the lab when the evaluation of the evidence will take place. And then the appearance, color, smell, consistency, and any other potentially identifying markers are being actually recorded. Some preliminary tests may be done for the initial identification, and we'll go over those in a minute, but most of them are not done on the crime scene unless there is an indication that the evidence may not last very long, or you want an immediate response because of the perpetrator or the suspect. You want an immediate response, or you need an immediate response. Especially for chemical evidence, there are some preliminary tests that can be done, roadside tests that can be done, spot tests, and those are color tests that can be done. And those are the preliminary color tests are mostly chemical reactions that lead to a color change, where our relatively small sample sizes are needed. They are relatively fast and inexpensive. They can be performed at crime scene with relatively little knowledge by the ones that are performing the tests. However, a significant drawback is that they are not reliable and they are not specific. The color change is not really objective. So especially if somebody is not directly trained, so sometimes it might be a change from a slight yellow to a dark yellow, or from a golden to a brown to a light brown, or something like that. So it's important here to always have a positive and a negative control also along with it. So for example, for cocaine, you would expect with cobalt thiocyanate, which is a common test, for it to turn kind of a purplish blue. However, if you do the same test for aspirin, you would see a kind of a pink color to turn. Now, somebody who doesn't know this would still see that there is a color change occurring, and would therefore conclude that, this person has something, there is something there because a color change occurred, but it's not actually the same color change. So that's a significant drawback of many of these preliminary color tests. The more reliable ones are the drug screening test kits that are often sold and found in pharmacies. The DIP test kits, so to say, that also rely on more of a biochemical reactions with an antibody test. So basically what happens here is that mostly it's urine tests, basically, and then these strips are dipped into urine, and the fluid runs up the strip, and then basically reacts with antibodies that are attached to the strips, and the specific drug basically is the antigen and reacts with the antibody. But they are also not specific. They are very sensitive, but they are not specific. So for example, somebody who is taking heroin, or who is accused of taking heroin but is actually taking oxycodone prescription, might cross-react with this test. So there is some interaction, or PCP is cross-reacting with ibuprofen or dextromethorphan. So there are some cross-reactivity between different drugs, and that is something that limits the reliability and specificity of these tests. So therefore, any positive test results of these preliminary tests should always be confirmed by a confirmatory test. And we'll talk about that in the next few slides. So when we talk about techniques that are used for the identification and quantitation, because the preliminary tests cannot quantify how much of a drug is actually present in the sample. They can only say, yes, this drug or this drug class is present. They cannot actually tell you how much of that drug is present. And there are three categories of drugs, or three categories of drug tests that have been classified. Category C is the lowest category. They are non-specific and they can at best identify a class. So in this category fall chemical color tests, the immunoassay or antibody test strips. You might know ELISA, for example, the enzyme-linked immunosorbent assay. Some of you might have heard of this. Another one that is not sold in pharmacies is the so-called RIA, the radio immunosorbent assay, which uses radioactivity and is a little bit more sensitive. And both of them can be used as a semi-quantitative technology, but they are not specific. They are sensitive but not specific. There is melting point if you know that you have a pure substance in front of you, but that you cannot guarantee with an unknown white powder or green powder or whatever powder you have in front of you. And then there's UV or fluorescence spectroscopy, and I'll go into that and explain that technology in a minute. There's category B, which are moderately specific. And those are primarily separation techniques. So basically you have a mixture of compounds and you just want to separate them out. I have to say it's probably better to close it here. Capillary electrophoresis. This is usually when we discussed in lecture 3, for those of you who remember that still, we separated out different DNA fragments after it was chewed apart through a PCR. This would be done via capillary electrophoresis, but you can also apply that to very small drugs that are separated out according to their weight, simply. And then there is what's called thin layer gas and liquid chromatography, and we'll go over the principle underlying chromatographic separation in a minute. Another technology or analytical technique that is in category B is microcrystalline tests, which are not separation techniques. And then there are pharmaceutical identifiers, and those are, for example, pill identifiers. So you have your pill, and usually it's stamped, obviously, and that gives a unique identifier, and that way you can identify the pill. The issue with that is that now we have counterfeit pills on the market that are stamped correctly but contain not what is actually stamped on it. So you shouldn't rely solely on just the pharmaceutical identifier just because the pill size is correct and the stamp on it or the identifier is correct. Category A are the specific ones, and these are mostly spectroscopic techniques aside from UV or fluorescence spectroscopy. And there we have Raman and infrared, which are using a very similar underlying light spectroscopic technique. Then we have mass spectroscopy, which we will go over later on. And then there's nuclear magnetic spectroscopy, which basically looks at the orientation of the nuclear spin of the electrons in the atoms that make up the whole molecule. So really the most specific one is category A. What we mostly have, though, is a combination of category A and B hybrid technologies. So we first have a separation technique that is then combined with a spectroscopic technique. And the most common one is a mass spectroscopic technique with a gas or liquid chromatographic technique. So that would be serving then as a confirmatory test. Either category C alone or in combination with category B are used for preliminary tests. So simply separating out the different compounds gives you not really a lot. It gives you the pure compounds that are coming out of the chromatograph at different times, but not much more. You need to combine it with something else in order to give you any information, really. So we'll go over that in the next few slides. So what is actually the minimum requirement for the unequivocal identification of a substance? So beyond a reasonable doubt, and remember that is one of the requirements in order for a jury to make a decision on a case and for a scientifically proven method. So a category A technique are of the highest scientific validity and specificity. So if we have that, then we only need one other method from either category A, B, or C in addition to that in order to prove the identity of a substance. Now, if we combine a category A technique with a category B technique, we can identify and quantify a compound. So that is ideal, and that is what is most commonly used today. If a category A technique is not available, and the problem is often with category A techniques that they are quite expensive because the instruments are so expensive, two unrelated techniques from category B and one other technique shall be used to establish the identity. And that can be sometimes a little bit challenging. You can do a microcrystal test, and then you can perform a color test, which would be category C, and a liquid chromatography in order to confirm the identity, but you cannot quantify it. Hyphenated techniques, which are most commonly used, and like I said, the separation and spectroscopic techniques are regarded as unrelated techniques. Running an LCMS will be sufficient to establish identity of a compound in most cases. That is what I refer to because they are unrelated. It's a combination of a category A and category B technique. It's a separation, category B, with a category A, the MS technique. And this was established by the Scientific Working Group for the Analysis of Seized Drugs. This is kind of the official organ for the Society of Forensic Toxicologists and also for the American Academy of Forensic Sciences in the United States. But beyond that, they are also working with other organizations around the globe to establish a set of standards that most agencies can adhere to and follow. So, category C tests for chemical evidence. We talked about color tests, and I mentioned chemical reactions between drug or drug class that results in change development of color. And this is kind of one of these decision trees. If it's positive, if it's negative, you go down from there. There's the classical alkaloid test, Myers, Wagner's, or Dragendorf's test. Dragendorf is probably the most common one here. And then if it's positive, you go further down and it gives you kind of the decision tree. Marquis test distinguishes between the opioids and then further the cocaine and the amphetamines. And then the Zwicker test gives you some of the barbiturates. Mandelin test rules out aspirin and some of the benzocaines. So there is some stuff that you can do with this, but it really only serves as an indicator for drug classes. And if you look at this, this would be, for example, a positive for the cobalt thiocyanate test for cocaine. And this would be a positive for amphetamine in the same test. So if you just look at this, somebody who looks at this looks kind of greenish, bluish, and this looks more purplish, I guess. One other issue with these color tests is that often they change over time. So many of them turn grayish, especially with the cobalt thiocyanate test, after just a few minutes. So you really have to pay attention to them. Another one is the immunoassay antibody test kits, and the ELISA is really the one that is most commonly used because it's relatively easy, relatively fast to perform. They strip test kits, so you can't really do that much wrong. Sometimes there's higher throughput with plate test kits, and they often now done today as preliminary tests, even in toxicology labs after the tests have arrived, because you want to kind of optimize the throughput in the laboratory. The RIA is not done because it involves obviously the use of radioactivity, which is hard to get rid of. You have to kind of cordon off an area of the lab specifically for that to work with, and it has several restrictions. It detects very low amounts, so it's very sensitive, but once again not very specific. So there's cross-reactivities. Other similarly structured drugs may also react positive. So you can narrow it down, but you cannot exclude necessarily all other drugs. So the way it works is your drug is basically the antigen, and you attach your antibodies to the plate, and then you create kind of a sandwich where your antigen, your drug, is kind of sandwiched in between your antibody that is attached to the plate, and then you also add antibodies that also have the same affinity for that specific antigen, your drug. And attached to that loose antibody that you add to the solution is actually an enzyme. And in most cases, that enzyme is horseradish peroxidase. And then you remove all of the loose enzymes and everything else that is floating around. And then you add a solution with which the enzyme reacts. And then that will result in a color change, enzymatic reaction, and it's only equivalent to the amount of enzyme that is actually present in the solution, and that will indicate to you how much of the drug is actually present, because that only depends on how much drug is actually sandwiched in between these two antibodies. So it's quite simple. So you can kind of semi-quantitatively tell how much of the drug is there. It's a fairly simple approach. In most cases, though, what you get in the pharmacy is basically just a cutoff value. So the cutoff value would be 50 nanograms per milliliter for amphetamines, or 200 nanograms per milliliter for this and that, or 25 nanograms per milliliter for THC, or something like that in urine. Below that, it's going to give you a negative result. Above that, it will give you a positive result, but it won't quantify it for you exactly. Another category C test is the UV, ultraviolet, and then also extending into the visible range. Ultraviolet range is from 200 to 400 nanometer. And if we were to meet in class, I would ask you the question, which one is the most energy intense light? Is it UV, is it visible, or is it IR? And if you think about it, we are wearing UV protection, sun protection when we go to the beach, but we're not wearing IR protection or visible light protection. Visible spectrum light protection would be a little bit insane because then we couldn't see light or anything at all. So 200 to 400 nanometers is UV, and that is actually the highest energy light that we utilize for the detection of compounds. So this is the most energy intense wavelengths that we're using. 400 to 800 nanometers is visible light range, and then anything above that is IR, not anything above that, but 800 to roughly 4000 is IR. With UV and visible, we can actually quantify and detect compounds, but really with limited specificity. The absorption range of chromophores and oxychromes is indicative of functional groups. Now, ultraviolet, like I said, 200 to 400 nanometers is obviously a relatively brief range. And then you've got the visible range, which is 400 to 800. Then we've got infrared, which is a lot wider. And then we've got the microwaves, radio waves. And before that, we've got X-rays. And this would be the spectrum of diazepam. And you see, in terms of absorbance, there is a maximum here at around 230, and then another one around 280, something like that. You see how they are like these lambda maxima. That's the wavelength maxima. So you would want to measure, in order to quantify, you would want to quantify it either at 230 around that or at 280 for diazepam. But it's not specific to diazepam. So let's take lorazepam, or let's take some other benzodiazepine. They would look very similar to this. So it's not all that specific to your drug. It's rather general. I don't know, do I have another one? No. I thought I had like methamphetamine or something like that. What you need in order for a compound to give you any UV spectrum is double bonds. You basically need some kind of what's called a chromophore. So for example, in order for a compound to absorb any kind of light or any kind of color, for example, for this pen to be kind of orange like this, vitamin A, you would need a number of double bonds in it. And for those of you who might remember the structure of retinoic acid or something like that, you remember that there are a number of double bonds in it. And that is basically creating a nice interspersed double bond system where a charge can be distributed. So the outer electrons can be elevated to a higher electron state, and when they fall back into their ground state, they actually give up energy. And the absorption here is actually the one that is being registered. So once the energy is being absorbed, that is when UV light is registering it. We also have fluorescence. That is when the energy is being dispersed again, is being given up when it goes back into its ground state. And that's the excitation wavelength and emission wavelength. So the excitation wavelength is the one that we are looking at here. That is the absorption. And then the emission would be when somebody fluoresces. And fluorescence is something that is much less common. Quinine, for example, is a great example. It fluoresces. It has kind of a natural fluorescence. For those who like Schweppes, not the ginger ale, but the tonic that has quinine in it, that actually fluoresces. So if you put it in and shine a UV light at it, then it will fluoresce. There's another category C test, microscopic identification. And the most common use of it is obviously for the identification of marijuana or cannabis. There are a few specific hallmarks of marijuana plants, and most commonly are the so-called monolithic hairs, these ones here, these little spikes that you see on the female plants that are very common, and then these oil-filled glands that are surrounded, the trichomes that are surrounded by these little fillers. So you see these little oil-filled glands here. And that's where the high concentration of THC is, because THC is so lipophilic. It's mainly concentrated in these little oil-filled glands. They also have cystolithic hairs, and those look like little spikes when you look at it. And that's basically a very strong identifying mark for THC. Microscopes may also be used for category B test, and that would be microcrystalline tests, and that is then categorized as category B. And basically what is done here is that you have a hypersaturated solution of your drug. It has to be a pure drug. And then you let that drop of your hypersaturated solution slowly dry out, and you see how it crystallizes out. And this here, for example, is, I think it's cocaine, but I'm not certain. I'm not 100% certain. And the way it crystallizes out is specific to the drug. There are much more impressive ones. I once had some that looked just fantastic, phenomenal how they crystallized out. There are not a lot of people who do microcrystalline drug identifications any longer. It's really an art form today. You need a lot of experience for that, and that's why not a lot of people are doing it any longer. So, probably the most common one that is being utilized today is the separation techniques, and specifically the chromatographic techniques. And some of you may have done this over the years, or even as far back as kindergarten or elementary school, when you used like a marker pen like black or something like that, and you just put it on a filter paper or just a paper, and then put a drop of water in it and concentrically looked at what happened to a black marker. Because it's not black actually, black is not a color, it is composed of various different colors, and concentrically you see a diffusion, and you see like purple or green or blue or something like that diffuse out of it. Originally though, chromatography was developed based on the separation of plant components and chlorophyll, carotenoids, and stuff like that. So you see here, you kind of apply a whole extract from a leaf, and you see how it all separates out so nicely here. This is a wonderful chromatogram of different leaf extracts, maybe from different seasons, because the carotene content is so much higher in some of them, which usually indicates that it's more towards fall. And this just evolved into a very highly sophisticated system which separates compounds based on their physical chemical properties. This can be by ionization, which is then an ion exchange column. It can be the partition, and that is really the main kind of application today. Partition between two different phases, a lipophilic and a hydrophilic phase. Or it can be the size of the molecule. Larger molecules just bump more frequently against different obstacles, whereas smaller molecules are just racing, they can race between all of these obstacles, and that's called size exclusion. But really the partition between the lipophilic and a hydrophilic, what is the molecule attracted to, the affinity separation, affinity chromatography is the one that is most commonly used today. And the first one that was used was the thin layer chromatography, and then that was the stationary phase that did not move was silica. And silica back then was attached to glass, and later on, because glass is not really all that cheap, it became aluminum. And silica obviously is quite hydrophilic. It has many hydroxyl groups on the surface. And what happened then over time is the solvent here is the mobile phase. So the stationary phase doesn't move. The solvent is the mobile phase, and basically here they have these three dots. And then the solvent, through capillary forces, moves up the stationary phase, and whatever moves has a more affinity for the mobile phase moves up higher on the stationary phase, because it distributes more in the mobile phase. Whatever has a higher affinity for the stationary phase is more held back and is not moving as fast along. And therefore the blue dots have a higher affinity for the stationary phase than the yellow dots, and the kind of reddish dots here, magenta dots, have more of an equal affinity, you can say, for either phase. So when we look at silica as the stationary phase, silica is nothing else than sand, basically. And it's highly purified sand, so it's very structured sand. And basically what you have on the surface is basically just free hydroxyl groups. And these are obviously going to be ionized. They will all be basically negatively ionized. So everything that is ionized itself, positively ionized, will stick to it, will attach to it very strongly, and will be held back. So this is called also a normal phase silica, hydrophilic. It's very hydrophilic. What we do today is that we change the polarity of the stationary phase, and we do that by end capping. This is called end capping, these free hydroxyl groups at the end of the silica. And this can be done with just hydrocarbon chains that range from C4 to C18. C18 is usually the standard, and C18 is then called RP18, reversed phase. Reversed phase 18. And this end capping basically reverses the process. So instead of being hydrophilic, now the stationary phase is hydrophobic. So this is called reversed phase silica, and that is lipophilic. What's the purpose of this? Now this requires a little bit more explaining. So bear with me, and you might have to rewind and listen to it again. Normal phase silica in hydrophilic is hydrophilic. So if these are all quite charged and water friendly, and basically anything that is charged will be held back, then your mobile phase, the solvent here, needs to be the opposite of that. So you would use an apolar solvent. You would use something like toluene, like benzene, anything that is not charged at all. Flammable too, unfortunately. So that makes for not very environmentally friendly mobile phases. Furthermore, there is not a lot you can modify about that mobile phase. You cannot, because it doesn't contain water, you cannot adjust the pH. So you cannot change the degree of ionization. You cannot change anything about it. You cannot change the pH, you cannot adjust the pH. So any compound that is in it, you cannot adjust their degree of ionization. So it makes it quite hard to play around with the parameters of your mobile phase or your stationary phase. In reversed phase, lipophilic stationary phase, you have that option because now you want your mobile phase to be aqueous. And now you have water with sometimes a little bit of modifier like acetonitrile or something like that in it. But in basic principle, you want it to be a water-based mobile phase. And that means you can add a buffer to it that can be adjusted in pH to whatever you want it to be. In addition to that, most compounds, especially when it comes to drugs of abuse or pharmaceutical compounds, are carbon-based, right? So most of them are by nature relatively lipophilic if they are uncharged. So they actually prefer a lipophilic environment in which they can nestle. So a normal phase silica, they would just all go right through and mainly distribute in the mobile phase with a normal phase silica. But if you reverse it, they will stick to the mobile phase. Now, most of them also have a functional group, so you can actually modify their behavior. You can impact their degree of ionization, and that allows you to separate them out very nicely based on how much they are ionized. So very nicely reversed phase chromatography allows you to separate out compounds very nicely, much nicer than normal phase silica would ever allow you to do. So, thin layer chromatography, it is very inexpensive, but it's usually quite time consuming because you need to apply the compounds one by one. You need to, I have to do it because I deal with natural products, but it doesn't allow for high throughput. And instead of a layer of silica, basically what has been done in HPLC, high performance or high pressure liquid chromatography, you use not a layer of silica, but you pack a column with little spheres of silica. And usually they're like 5 micrometers, and you really pack it very tightly. And that basically gives you a very high resolution, because now you can pack this column is packed with silica, and you pump with very high pressure the mobile phase through this column. The pressure that you usually achieve in HPLC is around 200 to 300, 400 bar. So we're talking about 200 atmospheres that you can pump through that column of mobile phase. So what you would never be able to achieve, obviously, in terms of separation of compounds. And then you have at the end, because the separation alone would obviously not allow you to detect these compounds, because many of them are not, you wouldn't be able to see them with your eye. It's just eluting coming out with your mobile phase. You would have to have a detector at the end. And that can be a UV detector or a fluorescence detector if you know the properties of your compound or compounds you're looking for. But in most cases today, it will be a mass detector. And that allows you to pretty much look for whatever compound you're looking for. And so once the compounds exit the column, you will be able to see them. And this is a comparison of the TLC versus the HPLC. So you see in the TLC how the separation happens, and the nonpolar compound exits first. So this is a normal phase, TLC and HPLC. And you see the yellow compound runs through the fastest, and here it comes through first, and then the red, and then the blue. So blue is retained the longest. They are the most polar, and yellow is the most non-polar. And this would be then considered the retention time. So this is time here on this axis, on the y-axis. And on the x-axis. On the y-axis, we simply have our signal, our response. I'm sorry, my handwriting with the mouse is quite poorly done. So this is how TLC translates to HPLC. It's really marvelous how this has been done over the years. In the olden days when I went to school, we had to hand pack these columns with silica. These days they all come pre-packaged, and makes for a huge difference in terms of quality. And this is basically how the HPLC instrumentation looks like. Everything is pretty much integrated. This is a fairly old instrument, but it's still very much integrated. This is with a UV detector. You have your solvents here on top. This is your mobile phase. Then there is a pump that can resist this high pressure, because you're looking at pressures of 200, 400, sometimes even much higher pressures, because there's now what's called ultra pressure or ultra performance liquid chromatography, which shortens your runs even further to just down to a few minutes. It's amazing. Then you have your sample injector and your HPLC column, and a detector at the end, and then to waste, and from the detector it goes to a computer. In the old days, once again, just to let you know how good we have it today, this chromatogram or this computer was actually just a printer and not digitally displayed, so it was just printing it out. So, to repeat, normal versus reversed phase in chromatography. If you look at normal phase, we have a hydrophilic stationary phase, basically just silica, and a lipophilic aprotic or hydrophobic mobile phase, like benzene, toluene. You just have to think of fire and you're already on fire. So hydrophilic compounds will interact more with the stationary phase and will be retained on it. They will be retained longer on the silica at the bottom of the plate and not advance as fast. And basically, if we look at testosterone here, you see how long the run is, 30 minutes. Prednisolone is eluting last, so this is retained the longest, whereas methyl testosterone is retained the least, so it elutes first, followed by testosterone and norgestrel, medrizone, and then 5,6-cortisone and hydrocortisone. So this gives you an indication of what is most lipophilic, methyl testosterone, to most hydrophilic, prednisolone. And here you have your mobile phase, N-heptane and 2-propranolol. If you look at reversed phase, now everything is switched around. It's a lipophilic or much less hydrophilic stationary phase. The silica is in huge part end-capped with long hydrocarbon chains. I say in huge part because some of the end capping is never 100%. So not all of the hydroxyl end-placed groups are replaced or end-capped with the hydrocarbon chains. It's much more versatile, allowing for mobile phases that can be modified with buffers, and therefore the pH can be adjusted. So here, lipophilic compounds are actually interacting more with the stationary phase, and they will be retained longer on the reversed phase silica. So now you see, first of all, we can cut down on the run time by 10 minutes. If you're going through like 70 samples, that saves you 700 minutes there. And you see that the separation is a little bit different. 6 and 7 now, hydrocortisone and prednisolone are not separated. But cortisone, then you have testosterone, you have methyltestosterone. So the order in which the compounds are eluting from the column are different. So now all of a sudden, norgestrel is actually the most hydrophobic. It's retained the longest, so it's a little bit different, definitely different from this. So they used here a UV detector. You can see they did not have to use a mass spectrometer for detection. Okay, so this is really the separation techniques have so far advanced over the years. It's a fascinating topic. I could talk about it for hours, but I have already spent a full hour on this, so I don't want to keep you much longer. Okay, so microcrystalline. This is actually methamphetamine. So it looks really beautiful, and there was once a website from the University of Central Florida which had a whole collection of these crystalline formations. It was beautiful, but then I think they took it down, unfortunately. So basically, I already mentioned most of this. So it's basically a drop of the dissolved drug sample is mixed with a reagent and then slowly dried under microscope, and the formation of crystals are observed. And the crystal formation is really specific and can be used as a confirmatory test for drug identification. But as said, it really requires a lot of experience, and it needs to be a pure drug, because otherwise you get all kinds of crystals that really form differently and makes the identification complicated or impossible. So spectroscopy. The range of spectroscopy here gives you an overview of, when I mention UV is the highest energy that we utilize. X-rays is more energetic than that, and then the gamma rays obviously are even more energetic than that. IR is much less energetic than even the visible light. Spectroscopic techniques are very commonly used for the detection and identification of drugs. And usually we talk here about the interaction between matter and energy of a certain radio frequency. This applies to UV and IR in particular. It doesn't apply to mass spectrometry though. Ultraviolet causes the excitation of electrons on the outer shells of atoms, the valence electrons in molecules. So the energy that is absorbed by the atom and the molecule is of a specific wavelength. I indicated that by giving you the spectrum of diazepam and pointing out the wavelength maxima. And the visible spectrum allows us to actually see light of different colors. The UV visible light is not compound specific, but it allows us to potentially narrow it down to specific drug classes. Now, when we look at IR, this is a little bit different. IR is actually a confirmatory technique. It falls within the category B. And that is because here we do not stimulate the valence electrons, but rather each atom in a compound is stimulated together with its neighboring atom together. So the bond between two neighboring atoms is stimulated. And for example, here in this one, it's cocaine base, yeah. So here, for example, this one here is it's an ester bond. You see that by the double bridged here. So everything out here is usually has to do with oxygen. And the way that an ester bond is kind of vibrating, the neighboring double bond is kind of can stretch in various directions. So it's just the bond between two neighboring atoms and how they can stretch and come closer and further away from each other and kind of twist around each other. That is detected by IR. And then you have here in the closer one range here, for example, at 1750, yeah, around this range, it's not linear, as you can see, 2000 to 3000. This is the N bond, 1750 around, and this is the N bond. Cocaine base has an N bound, an NCH3 bond. This is recorded there. So this allows you to really classify specific bonds in a molecule. And then as you get closer here to this range, anything below 1000, that actually gives you kind of a fingerprint region for overall molecular vibrations. So it's kind of like more how the overall molecule vibrates. You can compare this spectrum, the IR spectrum, to a sample, a pure cocaine-based sample that you have in a database, and it should basically look identical. Cocaine base looks different from cocaine salt, the hydrochloride salt, so you can distinguish between these two. A drawback, obviously, of IR is that you need a pure sample. IR can usually not work with a mixture of samples. There is, however, a technique similar to IR. It's called Raman, and Raman allows you to even test for specific substances in mixtures on surfaces. So, for example, what was done here is you see various Raman shifts. So it's basically what you see here with IR just turned upside down. And you see the fingerprint region here again, and then it looks a little bit different because the stimulation or the excitation is a little bit different, but it's very similar in how it works. And what you see here is basically here is a comparator of pure cocaine. And what they did here, they have a fingerprint, and they used Raman, and it's Raman scattering. So you have basically you use Raman light, and then you have a detector that is, oh, you can't see it, I'm sorry, I'm doing something off camera here. So it's basically a Raman detector that allows you to, it's just on the surface, that allows you to directly look at, it's a laser, that allows you to directly look at the surface of an object, and whatever is scattered away at a particular angle allows you to detect that wavelength, and through it's called a Fourier transform. It's a mathematical procedure It is being utilized to transform that into a particular spectrum. And in this case, they compared pure cocaine to a fingerprint before and after lifting. And in both cases, they were able to identify cocaine that was left on that fingerprint, that was part of that fingerprint. Obviously, as you can imagine, the amounts of cocaine that were left on that fingerprint are infinitesimally small. So it's astonishing what can be done today. It must have been just a little bit, a little dusting of cocaine that was on that. But if you hit the right spot, you get enough of it that it can be identified. So you only really need maybe a few thousand molecules in order to identify cocaine on this particular fingerprint. So this is a significant development, Raman, for surface recognition of compounds. It doesn't need to penetrate the sample in any depth. And that is now being utilized for identification of all sorts of materials on surfaces. But I want to go to kind of the gold standard of identifications of category A identifications, mass spectroscopy. In contrast to the other spectroscopic techniques where we had kind of matter, energy, and the use of radio frequency, mass spectroscopy does not, I repeat, does not use radio frequency or light emittance. It does not use that. What we do here is it basically just uses ionized fragments of a molecule after the molecule has been exposed to a beam of electrons or some kind of charged matter. And those are the fragments that you see here that are recognized or detected by a detector. And that is once again cocaine. I just can't resist it. 303 is the molecular weight of cocaine, and this is the molecular peak of cocaine. And then we have the highest, the so-called base peak at 84. You might not be able to identify that right away, but cocaine I know in and out. And 182 is the other important peak for cocaine as a fragment. So basically what happens is you have your intact cocaine molecule. It is being separated on your HPLC column or GC column or whatever you use. It exits your HPLC column, your column. It enters your mass spectrometer, and then it is bombarded with electrons, with a beam of electrons, highly focused. You've got your intact molecule, it's bombarded. It takes on an additional charge and enters a vacuum. And that vacuum, that additional charge that you put on that molecule destabilizes the molecule. And that results in fragmentation. And once it enters the vacuum, what happens to a compound or any matter in a vacuum is that it just basically processes or progresses on the path that it has taken before. It doesn't change course. It won't do anything unless there is some kind of influence on it. Basically, the only thing that happens then to it is gravity will influence it. And that gravity depends solely on the mass of the fragments that are generated. And the fragments are then detected based on their mass by a detector plate. So the deviation from a straight course because it's basically a vacuum, as good as we can get a vacuum, the deviation from a straight course depends only on the mass of the fragments that are generated. Your molecule is breaking apart into these fragments, and the deviation from a straight course only depends on the mass of that fragment. And that then basically gives your detector the mass of that fragment. Now, the abundance that is on the y-axis, abundance, relative abundance, depends on how stable that fragment is. Remember that we added an electron to our molecule and that destabilized it. Now, with cocaine, you see that the molecular, this is basically the molecular or the fragment weight, there is only little left of the intact cocaine. It's only very small, the abundance of the entire cocaine molecule. But the fragment 84 has 100% abundance, so it's the most abundant fragment that just travels through the vacuum and is detected eventually when it hits the detector at the end. 182 is pretty stable as well. It has a relatively high abundance, over 50%, and there are some others here that you can see in here. The abundance, therefore, depends on how stable these fragments can maintain themselves. If they cannot rearrange or cannot stabilize themselves, then they break apart further. And this is where some of these other fragments come from. They're falling apart further. They are not very stable. They just fall apart further. So let me ask you then that. I know you have to kind of answer it for yourself. CH3. So this has to do with calculating the mass of fragments, right? So molecular weight of CH3 would be, carbon has a molecular weight of 12, right? 12 units. Hydrogen has 1 molecular unit. So 3 hydrogens plus 1 carbon make up 15, right? So 15 would show up here. I don't know if it's even still on here. 15 and then whatever abundance comes with it. So for our next lecture, I would like you to consider what would be an abundance of, let's say, 18. A molecular weight of 18, sorry, not abundance. Molecular weight of 18. What kind of fragment would you say that would be? 18. What fragment would be 28? Those two I would like to ask you guys next week. Important is that if you do not change the settings, the parameters of how strong the electron beam is, then the pattern of fragmentation will always be the same. So you will always get the same abundance of fragments, you will always get the same fragmentation pattern. So this allows you to really uniquely identify and unequivocally identify a compound using the mass spectrum that they generate. MS is therefore a strong confirmatory analytical technique, which is often then coupled conveniently with a separation technique, often chromatography, because you conveniently can separate all of your compounds in a mixture and then directly identify them and also quantify them. So this is really the most common forensic confirmatory analytical technique. GC-MS was always the gold standard, but now HPLC-MS, because it's slightly more versatile, is kind of sweeping in. And this is kind of how it looks like. And this is an GC-MS. Basically, there is a magnet in here, and the magnet actually deviates them from a straight line, and based on their mass, they are deviated from a straight line. Now, there are different kinds of mass spectrometers. Some are intentionally deviating them from a straight line. Others are letting them just transverse through through a vacuum, and then they are kind of just deviating from a straight line on their own in the vacuum. There are time of flight. There are all kinds of very different detectors out there. So it's fascinating. Once again, I could talk for a very long time about this. The last topic I want to discuss, and we are basically on our last page for this, is trace evidence. And trace evidence always sounds like something very mysterious because it has the word trace in it. So trace, you would think, must be tiny. But it actually does not necessarily define the presence of very low amounts of a certain substance. In contrast, the definition of trace evidence is any evidence that is left when one object gets in contact with another object. So it's Locard's exchange principle between the victim, suspect, objects, and the crime scene. Trace evidence is therefore any evidence that is collected at a crime scene. So it's not just what you would commonly or logically conclude is just small evidence, or that is only there in small amounts. Can be fingerprints, gunshot residues, hairs, material fibers, soils, paint chips, explosive residues, volatile hydrocarbons. These are all considered trace evidence. Sometimes we might classify trace evidence as something that is that needs to be collected in more of a it's more sensitive, or it's easier to be destroyed, or easier to get lost, or easier to degrade, but that is not necessarily the case. Just keep that in mind. Trace evidence is not the same as something that is present in low amounts. Okay, and this concludes our lecture 4. The lecture 4 quiz password is PORX. I don't want to give anything else away about that password other than may the force be with you. And I hope that those of you who have seen the movie yet enjoyed it. I have some concerns about it. I've seen it, but well, to each their own, I guess. Okay, in case you have any questions, as always, please ask on the discussion board. I will also obviously be available to address any questions that you may have during lecture 5. And the required discussion board post your responses will be made available shortly afterwards on the discussion board for lecture 4. Okay, that would be it. Thanks for listening. I think we filled up the hour quite well, and I look forward to seeing you, hopefully all then, during week 5, which will be January 16th, Tuesday, January 16th. See you all then. Take care, everybody.